So while I'm looking for that, let me explain acids, bases, and salts for you. So generally speaking, you are expected to know a few things about acids, bases, and salts. One, you need to know to define an acid, base, alkali, salt. So let's begin with the definitions. What is an acid? An acid is a proton donor, or an acid is a substance that produces protons in solution. Okay? Those things kind of mean the same thing, really. All right. An acid, and so that's an acid. A base is a proton acceptor, or a base is a substance that produces OH ions in solution. All right. Following so far? You guys still there?
Yes, sir.
CSEC Chemistry. Here we go. Okay, good. Okay, so the next thing we want to define is a salt. A salt. I tend to define a salt in more in the sense of what happens for a salt to form. So a salt is formed when the hydrogen in an acid is replaced by a metal or the ammonium ion. So let's see what we're saying by that. All we're simply saying is that if you have an acid, HCl, right, and you replace that with a metal such as sodium, you're going to get sodium chloride, and that's a salt. If you replace it with NH4, you're going to get ammonium chloride, which is also a salt. All right. So if you have sulfuric acid, H2SO4, and you replace the hydrogen with sodium, you're going to get sodium sulfate, and that's a salt. All right. If you replace it with NH4, 2SO4, you're going to get a salt as well. So once you replace the hydrogen in an acid with a metal or the ammonium ion, you get a salt. Now, how can I tell the difference between an acid and a salt, a base, an acid and a base? An acid turns blue litmus paper red. A base turns litmus paper blue. Okay? An acid is corrosive, it will burn you. Bases are not necessarily corrosive, but alkalis are corrosive, and I'm going to talk about alkalis soon. Acids conduct electricity in an aqueous solution. Okay? So sulfuric acid, that's why they use sulfuric acid in batteries, because it will conduct electricity. Acids have a sour taste, like vinegar. Vinegar is an acid, or lemons. Lemons contain acid. That's why they have such a sour taste. Citrus fruits, those things. Bases have a bitter taste. Bases are slippery to touch. So soap is made from bases. You take a base and you put it in some oil, heat it, and you get soap. Okay. Well, alkali really, not a base necessarily. So they're corrosive and all that. They have a pH, acids have a pH of less than 7, bases have a pH of greater than 7. Of course, 7 is the neutral. All right. Now, alkalis are bases that dissolve in water. It's easy to identify an alkali because they have OH. They're bonded to metals and they have OH, like sodium hydroxide. That's an alkali. Magnesium hydroxide, calcium hydroxide, ammonium hydroxide. Those are all alkalis because they have the OH there. Okay. So then now the situation is, what do acids react with? Acids react with bases. When an acid reacts with a base, what do you get? Salt and water. Acids react with metals, reactive metals. When an acid reacts with a metal, what do you get? Salt and hydrogen gas. When an acid reacts with a carbonate, what do you get? Or a hydrogen carbonate, you get a salt, water, and carbon dioxide. Okay, acids will also react with sulfites, SO3 2- ions. And when it does with that, you're going to get salt, water, and sulfur dioxide. You'll realize that every single reaction of an acid gives you a salt. Okay, all of them give you a salt. Give me a second. All right, so those are the reactions of acids. Then now, what do bases react with? Well, bases react with acids to produce a salt and water. Bases also react, well, alkalis, and this is the one reaction that is pretty serious. Alkalis react with ammonium salts. So NH4Cl, see, ammonium plus something like a sodium hydroxide to give you a salt, NaCl, plus water, plus ammonia. This is the one reaction that we say, look, you know that bases react with acids, but do you know that bases or alkalis rather react with ammonium salts to give a salt, water, and ammonia? You must know this reaction. Okay, it's pretty common. All right, so now that's that. Then now, for acids, bases, and salts as well, you need to know about oxides. Oxides, all right? So there are actually 4 different types of oxides. You have acidic, did I say 4? Yes, acidic, basic, neutral, and amphoteric, okay? Let's look at acidic oxides first. Acidic oxides are oxides of non-metals. In other words, it's oxygen bonded to a non-metal. So non-metals such as nitrogen bonded to oxygen, sulfur bonded to oxygen, right? Carbon bonded to oxygen, nitrogen, well, we have nitrogen already, bonded to oxygen. All of those elements have oxygen bonded to a non-metal. Now, what's special about these oxides is that they're called, oh my God, they're acidic oxides. They're called acid anhydrides. Acid anhydrides. So what happens is when they dissolve in water, so if I were to take sulfur trioxide, SO3, and I put that in water, what I'm going to get is sulfuric acid. So these oxides dissolve in water to give you an acid. So that's why they're called acidic oxides, because they dissolve in water to give an acid. The next type of oxides are basic oxides. These are oxides of metals. So sodium oxide, magnesium oxide, aluminum oxide. No, let's not do aluminum. Calcium oxide, right? These are oxides of metals, and these are bases. These are oxides of metals that react with acids to give you salt and water. So if they react with acids to give you salt and water, they are base. So these are oxides of metals that are bases. The next type of oxides I mentioned was neutral oxides. These are oxides that do not have, they have a pH of 7. For example, carbon monoxide and the very famous H2O has a pH of 7. Okay, water that is. So these oxides have a pH of 7. The next type of oxides would be the amphoteric oxides. Ampho means dual in nature in this context. So these are oxides of zinc, aluminum, and lead. What's so special about them? Well, the oxides of these 3 metals, they can react with both acids and bases to give you a salt and water. Okay, so they will react with both acids and bases to give you a salt and water. All right, so now, next thing now about acids, bases, and salt that you need to know is salt preparation. How do I make salts? How do I make salts? And I have a little graphic here. Let's see if I can find it very quickly. All right, so what you're seeing here are types of salts, right? Hello?
Yes, sir.
Okay. Types of salts. Okay. Slideshow. Okay, dogs. Okay. So your types of salts now. We're just going to go through. A salt is a compound. We know that when it's formed, there are ionics, the types of salts now. You have acid salts. So acid salts are formed when you have, let's say you have an acid that contains 3 hydrogens, right? So here you have H3PO4. Yes? The acid has 3 hydrogens and you're reacting that with sodium. The sodium can replace 1 hydrogen at a time. So you'd end up with sodium replacing 1 hydrogen. So you end up with NH2PO4. The sodium can replace 2 hydrogens. So you end up with NHPO4, like that. Or it could replace all 3 hydrogens where you end up with Na3PO4. So these acids which contain hydrogen, see the hydrogen there? They're called acidic salts because they contain a proton. So they will have a pH of less than 7. If, however, if all the hydrogens are replaced, like in this last situation, we call that a normal salt because it does not contain any protons. Okay, so you have your acid salt, you have your normal salt. You also have dibasic, well, normal salt. You also have you also have soluble salt and insoluble salt. Okay, so salts which dissolve in water and salts that do not dissolve in water. You have salts which contain water of crystallization, and you have anhydrous salts. So the salts which contain water of crystallization, the biggest thing about them is that you're going to see them with a dot XH2O. In this case, it's copper sulfate. So it's copper sulfate dot 5H2O, 5 moles of water. This water is water of crystallization. So you have anhydrous. Anhydrous means it does not contain any water. All right. So there, that's that bit. Now I want to get to methods of preparing salts. So when preparing salts, you must consider the solubility of the salt and the solubility of the starting material and the hydration of the salts. There are 4 ways you can prepare a salt: ionic precipitation, which is double decomposition, titration or neutralization, direct combination, or a displacement reaction. Okay, and that's the table of solubility. So here's a little flow chart to help you with preparing the salt. We're just going to go through and then answer the questions. So Okay, sorry about that. So here's our little flow chart. So remember I said you need to check if the salt is soluble. So is the salt soluble in water? If no, then you use ionic precipitation. Ionic precipitation, you mix two solutions, and then when you put the two solutions together, you're going to get a precipitate forming out of them. In other words, a solid is going to form out of the two solutions. That solid is the salt you're trying to make. So you would filter and leave the residue to dry. So that's your salt made. If the salt is soluble, yes, the salt is soluble. You ask yourself, is it a potassium, sodium, or ammonium salt? Okay. Yes, it's one of those. Then you're going to use titration. Okay. For titration, you're going to react an acid plus a base with a salt. All right. To give you your salt. Your salt is made. If no, it's not a sodium or potassium or ammonium salt, then you ask yourself another question. Is the salt anhydrous binary? In other words, is it a dry salt? It doesn't contain water of crystallization, and does it contain two elements? If yes, you use direct combination. Okay, so you would combine the two elements together like iron chloride. Iron is one element, chlorine is another element. So if I want to make iron chloride, I can just combine iron chloride in a certain way to give me my iron chloride. No, let's say that it's not a binary salt. No, it's not binary. It's not anhydrous, which means that it contains water of crystallization. Then you're going to use a displacement reaction. Metal plus acid, or insoluble base plus acid, or carbonate plus acid. When you do that now, you're going to filter to get rid of the excess reactants. Then the residue, the filtrate, you're going to evaporate, and then you crystallize that. Okay. Any questions about this? No. Okay. Are you guys there? Yes. All right. So let's look at some questions now. And that's salts, acid, bases, and salt, and the preparation of the salts. Here we are. Okay, here we go. So here's a question. Phosphoric acid, which is used as an additive. Are you guys there?
Yes, sir.
Okay, phosphoric acid, which is used as an additive in soft drinks, can react with sodium hydroxide to form both normal and acidic salts. Define the terms acidic salt and normal salt. So an acidic salt has protons in it due to the partial replacement of the hydrogens in the acid by a metal or the ammonium ion. That sounds long, but that's what it is. A normal salt has no, well, you would not say has no protons. You say a normal salt is formed when all the hydrogens are replaced by a metal or the ammonium ion in the acid. Actually, you can't use ammonium ion because the ammonium ion is an acid in itself. Okay. Okay, which one, write one balance equation for the formation of a normal salt and an acid salt when phosphoric acid reacts with sodium hydroxide. So what they're really asking you to do here is you're writing the one for the normal salt and one for the acid salt. So let's write the normal salt first. So sodium hydroxide will react with phosphoric acid, PO4, to give sodium phosphate plus water, right? And then your acidic salt could be NaOH plus phosphoric acid to give you NaH2PO4 or Na2HPO4 plus water for both of them. And then you balance that equation. Okay? So, excess consumption of soft drinks may lead to an excess stomach acid. Excess stomach acid. How is the problem usually treated? How do people treat excess stomach acid? They take antacids, right? Things which fight against the acid. Explain the chemical principles upon which the treatment you stated in 3A above is based. So basically, when you take an antacid, it contains something like sodium hydrogen carbonate. That is why it bubbles. I don't know if you guys know about that. That's why it bubbles. And so when you drink that now, it neutralizes the acid in the stomach. Okay, write an ionic equation for the reaction. So this basically is sodium hydrogen carbonate, plus HCl, because HCl is stomach acid. If you do bio, you know that, to produce sodium chloride, plus CO2 plus H2O. And you balance the equation, you insert your state symbols. So that's the equation they're looking for. All right, this is mole conf. This is this question is from sorry, energetics. This question is from energetics, and we did that. Okay, so we press on. Here we go. That paper was actually from 2007. This one now is from 2021. So let's see what this one is saying. It says acids react with metals and bases to form salts. John conducted experiments to investigate the properties and reaction of acids using sulfuric acid, iron, and sodium bicarbonate. Define each of the following terms. An acid is a proton donor. Salt is formed when metal, the hydrogen in a acid is replaced by a metal or the ammonium ion. All right. John dissolved sodium bicarbonate in water and tested the solution with red and blue litmus paper. The red litmus turned blue. However, the blue litmus paper did not change color. State one reason why the red litmus paper turned blue, but the blue litmus paper did not change color. Well, the solution is basic. So therefore, the red litmus would change to blue, but the blue litmus would not change blue because it's already blue. Okay. State whether the pH of sodium bicarbonate will fall within ranges of pH greater than 7. State whether the pH of sodium bicarbonate will fall within pH ranges of pH greater than 7. Yes, its pH will be greater than 7 because it is basic. Okay. Some students investigated, come on, the action of dilute hydrochloric acid using a sample of solid sodium hydrogen carbonate. One of the students suggested that the reaction would yield a gaseous product. Describe a test that could be used to identify the gaseous product. Well, it is sodium. It is sodium carbonate. So since it's sodium carbonate, then you know you're going to get carbon dioxide. How do we test for carbon dioxide? You bubble the gas through lime water, and the lime water will turn cloudy. That will tell you that it is carbon dioxide. You could also blow the bubbles of the gas over a flame, and if it extinguishes the flame, it could possibly be carbon dioxide. A sample of the gas was collected in the laboratory by downward delivery. State the physical property of the gas which supports the method of collection. Why would they collect this gas by downward delivery? They would collect it by downward delivery because it's more dense than air. How do I know it's more dense than air? Well, air in this context is oxygen, O2. O2 has a mass of 32. Yes, 32 grams. Carbon dioxide has a mass of 44 grams. So it's heavier and it's also more compact. So therefore it's denser than air. Air in this context means oxygen. Okay, so that's why they collected it by downward delivery because it's more dense than air. And we'll look at those things later too. Write a chemical equation including state symbols for the reaction between hydrochloric acid and sodium hydrogen carbonate. We have been doing this all morning. Okay, so HCl aqueous plus sodium hydrogen carbonate, which could be aqueous as well, produces sodium chloride aqueous plus H2O liquid plus CO2. Yes, and then you balance that. Your equation has to be balanced. All right. Some metals react with dilute acids to produce a salt and a gaseous product. Write an ionic equation for the reaction of magnesium and hydrochloric acid. So let's take it from the top so we can do this. Magnesium, which is a solid, reacts with hydrochloric acid, which is aqueous, to produce magnesium chloride, which is also aqueous, plus hydrogen gas, which is a gas. Remember I said, identify the species which are aqueous on both sides. Magnesium solid, magnesium aqueous. Hydrogen aqueous, hydrogen gas. Chlorine aqueous, chlorine aqueous. Get rid of that. Rewrite what you did not cancel. Magnesium solid plus H aqueous to produce Mg aqueous plus H2 gas. Anything which is aqueous must have a charge. Hydrogen here, positive. Magnesium here, 2+. Next thing you want to do is balance each element. 1 magnesium, 1 magnesium. 1 hydrogen, 2 hydrogens. Oh, so this needs to be 2. There you go. And that is your ionic equation. Okay? And then that's that. Now you are provided with samples of lead nitrate crystals and sodium chloride crystals. Plan an experiment to make lead chloride crystals. Write in your responses in the spaces provided. So you are trying to make lead chloride. The first thing you need to do is determine if lead chloride is soluble or insoluble. Is lead chloride soluble or is it insoluble? Lead chloride is actually insoluble. So if you want to make an insoluble salt, you must use ionic precipitation. So what's my procedure? First thing, combine lead nitrate and sodium chloride solutions. Step 1. Step 2, filter the mixture. Step 3, collect the residue. Step 4, leave the residue to dry. That's it. Then now we proceed. Apparatus and materials. Since you're going to mix solutions, you're going to need a beaker, you're going to need a stirring rod, you're going to need funnel, you're going to need filter paper, you're going to need conical flask. Okay? Precautions to be taken. This should include 1 experimental precaution and 1 safety precaution. Now, why they put this here, experimental precaution and 1 safety precaution, is students always used to come and say, boy, you know, wear gloves, wear lab coat, those things. Nothing that protects the experiment. So now they're basically saying you need to state something which protects the experiment. So what you want to do in this experiment is, of course, you need to wear gloves and your safety, your PPEs, but you also need to use a stirring rod when you are filtering your mixture. Okay, so you need to use a stirring rod when filtering your mixture. Another thing that you could do is ensure that you use equal amounts of sodium chloride and lead nitrate. You could also ensure that they are mixed thoroughly. And also, when you are filtering, you stir the mixture to disperse the solid, and then you filter, washing off any solid of the stirring rod while you're filtering. In other words, when you're filtering, yes, let's say you're filtering here, this is your thing, right? And this is your conical flask down here. When you're filtering and you're pouring, your stirring rod should be here, and you should be pouring onto the stirring rod, washing off anything on the stirring rod in here. Okay, so that's an experimental precaution. All right. Next thing now, discussion. In preparing lead chloride crystals, it is unlikely that the yield will be 100%. Discuss 2 reasons why this is so. Well, it should be clear. 1, you're going to lose product due to when you're filtering. You're going to lose product when you're filtering. You're going to lose product when you're transferring this solution, the mixture from the beaker to the filter paper to filter it. So when you're pouring, some will be left in the beaker. Some will be left on the stirring rod. Some of it will be blown away. So it's not going to be 100%. Okay? And so you can discuss all of those things to get your marks. All right? So that's acids, bases, and salts. That was in January 2012. Okay, so there you go. That would be the first half of our session for today. Do you guys have any questions?
No, sir, I don't have any.
Okay. In the next session, we're going to start with organic, and then we're going to look at reactivity and extraction, then uses of metals and then impact of metals on living systems. Okay, and then non-metals.
Okay, sir.
Right. So since it's now 11:30, yeah, we can start, but don't eat anything heavy because it's gonna make you want to sleep. We can start back at 12:30 or so, 12:45. Okay.
Okay, sir.
All right. All right, so welcome guys to the second half of this thing. Based on what you guys are there, yes? Based on what CXC has put out, where's my picture? You're expected to know about the, yes, introduction to organic chemistry and the reaction of organic compounds. Thank God they don't ask you guys about polymers, which is a stretch and stuff. So it's mostly about introduction. Organic chemistry, what is organic chemistry? Organic chemistry is the chemistry of carbon and its compounds, except the oxides of carbon, which are carbon monoxide, carbon dioxide, and carbonates. Everything else which contains carbon is considered organic chemistry. Okay, so except for those three things. So basically carbon can form chains. It has four. So because organic chemistry is really about carbon, you have to know a little bit about carbon. Carbon is the sixth element. Its electronic configuration is 2,4. It has 4 valence electrons. It's right there in the middle, halfway between 8 and 0. So it can, you're thinking it can gain or lose electrons, but really what happens most of the time is that it shares electrons. So carbon can form chains, and we call this thing catenation. The formation of chains is called catenation, right? Carbon can form single bonds, double bonds, and triple bonds because it has 4 valence electrons. So it can form single, double, and triple bonds with other carbon atoms, with oxygen, with halides, with hydrogen, with nitrogen. It will form triple bonds with nitrogen, single bonds with halides and hydrogen. And of course, it can form double bonds with oxygen. If it can form a double bond, it means it can form a single bond too. Okay? So that's carbon. There are many different organic compounds, many, all right? It's a whole lot. Now, because of that, and because it would be difficult to study each of them individually, we have placed them in groups. The groups are called homologous series. So each different type of organic compound is in a group called a homologous series. I tend to use the word class. So if throughout the session you hear me saying the class of compound, I'm talking about the homologous series. Okay. Now, since they mentioned that you need to know about the introduction to organic chemistry, then chances are they may ask you about homologous series and the properties of each homologous series and those things, or of homologous series in general. All right. So the different classes of organic compounds or the different homologous series that you're expected to know about are alkanes, alkenes, alcohols, acids, esters, really just those. You would interact somewhat with amides in the form of proteins or polyester, or nylon. You would interact a little bit with ethers in the form of polysaccharides, but they're not giving you polymer chemistry, so thankfully. All right, so what are the properties of the homologous series now? So each series has a general formula that represents the series. For example, CnH2n plus 2 is the general formula of alkanes. N represents the number of carbons. So if I have a compound with the formula C5H10, I can tell if that's an alkane or not. All right? I just take the number of carbons, which is 5, and put it in the formula. So it would be C5, 2 times 5 plus 2. So that doesn't fit the formula. So therefore, C5H10 is not an alkane because it doesn't fit that formula. All right. Now, alkenes would be CnH2n, right? And alcohol CnH2n plus 1, OH, acid Cn minus 1, H2n minus 1, COOH. Those are the general formula of those groups of organic compounds. Then now, each homologous series, there's a gradation in physical properties. What does this mean? What this means is that as you move along the series, as you move from carbon number 1 to carbon number 2 to 3 to 4 to 5, etc., you change from a gas to liquid to solid. Okay, so there's a general increase in the physical properties. And also, because you are changing from a gas to liquid to a solid, the melting point is going to increase, the boiling point is going to increase. Okay, the next thing is that the difference between subsequent carbons is CH2 or 14 grams. So let's show what I mean by that. In the alkane series, methane is CH4. Then you have C2H6, then C3H8. Okay, let's just use these three. Now, the difference between methane and ethane is CH2. If I were to subtract this from this, I would get 1 from 2, 1, so it would C, and 4 from 6, 2, CH2. If I would do the same here, subtract that from that, I would end up with 2 from 3, 1, and 6 from 8, 2. So the difference is CH2. The mass of CH2 is 14 grams because carbon is 12 and there are 2 hydrogens, which is 2 times 1. So that's equal to 14 grams. Okay, so that's another property. And next thing about the homologous series is that you can prepare each member in the group in a specific way. There's a general way for you to make all of them. Okay, so you can make methane the same way you can make propane. All right. So there's a general method of preparation of each of the elements in the series. And that's generally the homologous series. Just some things for you to remember as well, that there are prefixes for the number, for the number of carbon atoms that you have in a species. So if it has 1 carbon, it's meth, 2 eth, prop, bute, pent, hex, hept, oct, non, dec. Okay. And then you can add suffixes to those things for you to determine the group or the class of organic compounds that you're referring to. So if it is pentane, you know you're referring to an alkene. If it is propene, you know it's alkene, right? And if it is propanol, it's an alcohol. And if it is propanoic, then you know it's an acid. So that's the sort of thing. Okay, so you're looking at that thing right there. So in terms of introduction, there isn't much more for organic chemistry. Also, you need to remember that the compounds that you will encounter can be straight, branched, or cyclic, right? Then there is the issue of isomerism, and this one is not too bad. So isomerism really is the occurrence of species with the same formula but different structures. So look at this, for example, C5H12. That's the formula of the compound. I can draw it like this, 1, 2, 3, 4, 5. I can draw it like this, interestingly. Okay, or I could draw it like this, 1, 2, 3, carbon, carbon, H, 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 CH3, CH3, CH3. Okay, so there you go. You can draw it like that as well. So you will realize that these 2 species have the same formula. Each of them have 5 carbons. You can count it and see. And each of them have 12 hydrogens, but their structure is totally different. So we call these things isomers of each other. Okay, this sort of isomerism occurs for alkenes. Mostly. For you can have this in alkenes as well, but for alkenes, there is this thing called cis-trans isomerism, where you have the same group across the double bond. So you have a double bond, right? And you have a chlorine there, and then you have a chlorine there, and then let's put hydrogen there and hydrogen there. There you have similar groups, which is the chlorine. Chlorine is there on opposite carbons of a double bond beside each other, or carbons beside each other. So that's carbon, each of them is bonded to a chlorine. The chlorine is oriented in a certain way, meaning that they're diagonal to each other now. See, that's diagonal. When they are diagonal to each other, we call this a trans isomer. trans isomer. We can actually have the carbons on the chlorines on the same side like this, and hydrogen there, and hydrogen there. See, they're on the same side. And we will call this a cis isomer. So cis means same and trans means diagonal. Okay, so your examiner may ask you for that as well. Okay, but in terms of introduction, that is pretty much it. We will now get into some questions about organic chemistry. Are you guys there? Not hearing anyone.
Yes, sir.
All right, so let us proceed now. It says the structures of the organic compounds are shown below. All right, good. Compound A, you can clearly see is an alcohol. It has the OH on it, right? So you know it's an alcohol because of that. Compound B is an alkane and compound C is an acid. So what are they asking us for here now? They say that state the name of the homologous series to which each of the group compounds B and C belong. So B is an alkane, C is an acid. Good, we press on. It says here, compound A burns with a blue flame in oxygen. Write a balance equation for this reaction. So compound A burns with a blue flame and they want you to write an equation. And you need to balance it. So compound A is C. Compound A is C2. How many hydrogens are there? 2 for 6. C2H6O, right? And it burns with oxygen. So it reacts with oxygen to give you carbon dioxide and water. This is a combustion reaction, right? So they're tying in the reaction with the general stuff as well. So the easiest way to balance this equation is to just simply place numbers in front of the carbon and hydrogen on the right. How many carbons on the left? 2. So you put a 2 right there. How many hydrogens on the left? 6. This is already 2, so you need to put a 3 there. 3 times 2 is 6. Okay, then now you need to balance the oxygen. Over on the right-hand side, you have 3 plus 4, that's 7 oxygens. And then now, on the left-hand side, you have 2 oxygens there and you have 1 there. But if I multiply this by 3, that becomes 6 plus the 1, 7. So that's our balanced equation. Okay, that's how you balance these organic combustion reaction equations. So simply place the carbons, balance the carbon and the hydrogen first, then you balance the oxygen last. All right, so that's that. Then now we proceed. It says no, we did that. State which of the two compounds, A or B, is more soluble in water. Give a reason for your answer, A or B. So A contains the OH group, which makes it slightly polar. Now, because it is slightly polar, it will dissolve in water to some extent because water is polar and the rule for solubility is like will dissolve like. If the substance is polar, it will dissolve other polar substances. Compound B, on the other hand, it has nothing on it which makes it polar. It is non-polar. So it will not dissolve in water. So when you're answering this question, what you need to say is that compound A will dissolve in water. Compound A is more soluble in water because it is polar, or it is more polar than compound B. All right. And like dissolves like. So that was 2014. All right. State whether compound A or C would react more vigorously with sodium metal and give a reason for your answer. A or C. A was the alcohol and C was the acid. So which one would react more vigorously with sodium? Well, the acid would react more vigorously with sodium because acids tend to react with metals, reactive metals. If you remember that, we just did that a while ago. Acids react with metals to give salt and hydrogen gas. So it would react more vigorously with it because you could say that acids tend to react more with the sodium, or you could say that the proton of the acid is more readily available than the proton of the alcohol. But that answer really is not at CSEC level, right? So you wouldn't have to do that. But just simply say that acids tend to react with metals as your reason for the answer there. Okay, write a balanced chemical equation for the reaction of compound C with sodium metal. Compound C was, I wonder if it was propanoic acid. Okay, so we want to write a balanced chemical equation for the reaction of propanoic acid with water. So what do we have here now? We have propanoic acid, which is C2H5COOH plus sodium to give you C2H5COONA plus hydrogen. Okay, and then because that is hydrogen, you need a 2 there and you need a 2 there and a 2 there. Okay, so that would be your balance equation for that reaction. Describe one test that could be used to identify the gas that is produced in the reaction above. We have been seeing this quite a bit. Hydrogen is produced, so you know you put a lit splint in front of the tube and it will give a popping sound, which would tell you that hydrogen is being produced. Okay, all right. So we will proceed again to the next bit. Yes. Okay, compound A and C react together in the presence of a catalyst to form compound D. State the name of the catalyst and draw a fully displayed structure of compound D. So we are now diving in because it's very difficult. Well, it's not difficult, but it's more likely that you are going to be given a lot of things about reactivity in the exam. If you have seen any past papers, you'd recognize that question 1 is generally about things like redox or energetics. So you should really look this year for something on electrochemistry or energetics for question 1. Okay, one of those two things. Your question 2 then, it could be something like acids, bases, and salts. Okay, so something like that will come. Question 3 is organic. Then question 4, you can get something with respect to qualitative analysis or something like that. Question 5 is organic again. And then question 6 is probably going to be something about metals and non-metals, right? So because you have 2 questions on organic, one can be about the introduction to organic, about isomers and those things. And the next part might be about the reactions of the organic compounds. But in this question, they're tying in all of those things. So they're saying now that compound A and compound C, which is ethanol and propanoic acid, react to form an ester. And the catalyst for that ester is actually, what I was going to say is that you need to know the conditions and the reactants and products for each of these organic reactions. Okay, you have to know the conditions. The conditions are very important. See, they're asking you about acid here. The catalyst is actually concentrated sulfuric acid. Okay, and of course you will apply a little heat to that reaction mixture. And so that's your catalyst. Now, when they react, you are going to get an ester. Acid plus alcohol gives you ester. What they want you to do now is to draw the structure of the ester. Now, when you're drawing the ester, you need to remember the thing. Acid portion drawn first, named last. Acid drawn first, named last. So your acid was propanoic acid. So you draw propanoic acid, C double bond O, O, forget the H, C, C, right? H, 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 H. And then instead of the O, instead of putting on the H, what you're going to put on now is the alcohol portion, which was ethanol. So you just put on the 2 carbons of the ethanol. All right. So this is your ester. Acid portion drawn first, named last. So now they may ask you the name of this ester. So what you need to do is now divide the ester into acid and alcohol. So you split it right there. This is acid. This is alcohol. The alcohol portion is named first. So you need to count the number of carbons in the alcohol. 1, 2. Find the prefix for 2 carbons, which is meth F. So it is F. To that, you're going to add ethyl. Why ill? Ill. You're going to add ill. So it's ethyl. Then count the number of carbons in the acid portion, which is 1, 2, 3, 1, 2, 3. And the prefix for that is prop. So you put prop. Then you add anoic acid. So this is anoate. Anoate. Ethyl propanoate. That's the name of this ester. Ethyl propanoate. Okay. And of course, that would be the structure of the ester. They may ask you for the name further down. Let's see if they actually do. Okay, no. Okay, so they didn't. Next question, 2-methyl-butane. Somebody saying? 2-methyl-butane and pentane are structural isomers. So this question would actually come under introduction to organic chemistry now. This is an introductory question. All right, so this now is an introductory question. Right? 2-methyl-butane and pentane are structural isomers with molecular formula. We actually just looked at it. C5H12. Define the term structural isomerism. So for you to define this, you're saying that structural isomers have the same molecular formula, but different structural formula. Your examiner is looking for those words, keywords, same molecular formula, but different structural formula. Okay? And that's what they're looking for. Draw the fully displayed structure of 2-methyl-butane. So they want you to draw the structure of 2-methyl-butane. So let's look at it now and dissect the name to show you how you can get the structure. You have to start from the right and work your way to the left. So the first thing is an alkane. It's butane. Okay, so it's butane. How many carbons are present in butane? 4. How do I know it's 4? Because but is the prefix for 4 carbons. So you draw 4 carbons in a chain like that. All right, it's an alkane, so there are no double bonds or anything else. Then now it says methyl. There's a methyl group somewhere. Where is that methyl group? It's on the 2nd carbon. So on the 2nd carbon, we're going to draw a CH3. Okay, is there anything else? No, there's nothing else. So you just fill in the rest of the structure with hydrogens. Okay, and this will be your displayed structure of 2-methyl-butane. All right, that's how you work that one out. So let us proceed and see what's next.
Mr. Why did you place the CH3 on the 2nd carbon?
Because in the name it says 2. So because it says it, basically this is saying that I have, if I were to write this in words to some extent, I could say this. I have a 4-carbon alkene that has on the 2nd carbon a methyl group. Okay, I could say it like that. So that's why I placed it on the, that's why I placed it on the 2nd carbon, because it says 2-methyl. Okay.
Sir.
So we proceed now. Draw and name one other structural isomer of C5H12. So we can draw and name one other isomer. We could actually draw a simple one, which is pentane. So you draw 5 carbons in a straight chain, 1, 2, 3, 4, 5, and then you just add hydrogens. All of these lines are hydrogens. I am not adding them now because hydrogens are annoying to draw, but you have to add them when you are drawing it. Okay, so this would be another isomer of C5H12, and this is pentane. 1, 2, 3, 4, 5. 5 carbons in a chain. All right. So that's another isomer. Remember, this would come under Introduction to Organic Chemistry. That was 2021. Well, okay, ethanol undergoes various reactions. So now we're looking at the reactions of organic chemistry. Depending on the reagents and conditions of the reaction, products with different functional groups can be formed. What is the functional group of ethanol? So I didn't mention this, but one of the ways that you can identify an organic compound is by this thing called the functional group. The functional group is the reactive part of the organic compound. It's the reactive part of the compound. Okay, so in the case of ethanol, it is OH right there. See, it's right there, OH. If it was an alkene, it would be the carbon-carbon double bond. If it is an ester, sorry, an acid, it would be C double bond O, OH. Okay, so that's the functional group of those species, right? So the functional group is the reactive part, and that's that. You would just simply, what is the functional group? The reactive part. Table 2 now. Sorry. So table 2 now. Table 2 summarizes the conditions and products of 2 reactions of ethanol. Complete table 2, inserting the reaction conditions and drawing the fully displayed structure of the products, which would be formed. Take note that the type of product to be formed is given in the table. So here you go. There's no reagent there. The condition is there. The product is an alkene. So in other words, how can I convert ethanol to an alkene? And which alkene will I get? Well, the fact is that if you have ethanol and you're converting it to an alkene, you cannot create or destroy matter. All right, you can't create or destroy matter. You can only transform it from one form to another, which is what we're doing here. So if you have ethanol, it can only be changed to ethene. Okay, and the conditions for that reaction would be phosphoric acid. Well, it's a dehydration reaction. Sorry, it's a dehydration reaction. So therefore, you're going to need not phosphoric acid, but sulfuric acid, right? Sorry, give me a second. You're going to need sulfuric acid and 170 degrees Celsius. Okay, so you're going to use conc sulfuric acid, H2SO4, those are square brackets, and 170 degrees Celsius. The alkene that you're going to get is ethene, so therefore you simply draw ethene. Remember, they did say you need to draw it. Okay, so that's what you would get. Now, pushing on further down, they say that you have your reagent over here. This is ethanoic acid now. That's ethanoic acid. You have to know to recognize these things. So that's ethanoic acid, CH3COOH. What's the condition for this reaction? The condition is actually the same as the one above. It is sulfuric acid, H2SO4, and you heat it. And you get an ester. The ester you get would be ethyl ethanoate. Ethyl ethanoate. These things you have to like get them off the top of your head very fast. So that would be this C, hydrogen, 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 carbon, hydrogen, hydrogen, hydrogen. Of course, you'd have to put in the hydrogens. I'm just drawing the lines to show the hydrogens now. So that would be the structure of your ester, okay, which is ethyl ethanoate. We know it is ethyl ethanoate because we can divide it into acid portion and alcohol portion, right? Then you name the alcohol portion first. It contains 2 carbons, so that would be ethyl. And then the acid portion contains 2 carbons, so it is ethanoate. That's how we get ethyl ethanoate. All right, so that's that table. Let's see now if you have invariably, you know. So you can go on, that's 2021. Figure 5 says, refers to the following reaction scheme. I like reaction schemes because they're very nice. Anyway, A, B, C, D, carefully consider the reaction scheme in figure 3 and answer the questions that follow. So when you look at a reaction scheme, as usual, mentally speaking, automatically your eyes go to the center of the scheme, which is where it should go. Okay, that's where your eyes should go first. So what you want to do is you want to look at the compound you have in the middle and see the transformations which are taking place with it. In this molecule, we have in the center an alkene. We know it's an alkene because there it is right there in the middle, carbon, double bond, carbon. For reaction 1, this alkene is converted to this up here. So you need to look at what's the difference between my compound, compound A, and compound B. Well, the differences should be very clear. So it's kind of like you're subtracting or canceling out and see what remains. You should recognize that hydrogen, this compound has 2 more hydrogens than this one. So actually, this is hydrogenation of an alkene. Okay, so we'll leave that there. For part 2 now, reaction 2, what's the difference between this compound C and this one? This has 2 bromines on it, Br2. Okay, so this is a bromination reaction or a halogenation reaction. Then now, what's this down here? Carbon dioxide and water. This is combustion. Okay, that's combustion. And then over here, you have this species. Once you see these, the species and the square brackets there, square brackets with the N right there, it's a polymer. Okay, this is a polymer of compound A. They shouldn't give you anything about polymers because they didn't say that's going to be on it, but who knows. Right, anyway, so let's see what the questions are asking us now. So we'll have to clear out. No, let's not clear. So let's see what the questions are. Identify the types of reactions numbered 1 to 4 in figure 3. So we kind of just did that. Reaction 1 is a halogenation. Reaction 2 is a bromination, or reaction 1 is a hydrogenation. Reaction 2 is a bromination, or you could say halogenation, since bromine is a halogen. Reaction 3 is combustion, and reaction 4 is polymerization. All right, so that's that bit, 4 marks. Nice. It says identify suitable reagents and conditions necessary, which could be used for each of the following conversions. Compound A to compound B. So let's go back up and look at compound A to compound B. So if I want to change compound A to compound B, that's a hydrogenation reaction. What do I need? I need nickel, platinum, or palladium catalyst. Okay, that's what I need. I also need hydrogen. I must have hydrogen. Then I will also need probably about 0 to 5 atmospheres, 450 degrees Celsius. When you look in textbooks, you might say, sir, but you know, when I look in a textbook, I don't see those exact conditions. Well, you will not see those exact conditions because the conditions can change somewhat, but what you will definitely see is nickel, platinum, or palladium catalyst. The temperature might change, the pressure might change. So you may see high temperature, low pressure, or low pressure, high temperature, but you will see a catalyst such as nickel, platinum, or palladium. This textbook that I have in front of me is saying nickel catalyst, 5 atmospheres, 150 degrees Celsius. But in other textbooks, you will see 0 to 5 atmospheres, 450 degrees Celsius, platinum catalyst, those sort of things. Okay, so those would be the conditions for the reaction, and you have to know them because clearly they're testing you for it. Compound A to compound C. So let's see what this one is now. Compound A to compound C. All right, so compound A to compound C now, you actually don't need any reagents or conditions. All you need is compound A and bromine. Okay, that's all you need. Bromine in, well, aqueous bromine, and you bubble the gas through it. That's all, because this compound is probably a gas. Compound A is probably a gas. So you just bubble it in aqueous bromine, and you should get your product. So you don't really need anything for that one. All right. So we proceed. So next, see now. It says now, given that R is an ethyl group, state the molecular formula of compound A. They say R is an ethyl group. Ethyl, so R is an ethyl group. So state the molecular formula of compound A. So in other words, this compound, I'm going to take it out, right? And they're saying that R, so the R right there, it is ethyl. Now, methyl, the general formula of these groups called ILs, alkyl groups, is CnH2n plus 1. So methyl, meth is carbon number 1. So we're going to replace N with 1. So it is C1, H2 times 1 plus 2, right? So that's equal to CH3. Ethyl is carbon number 2. So we're going to replace N with 2. So it would be C2, 2 times 2 plus 2. So that's going to be work out to 5. So it's going to be C2H5. So this R is actually C2H5, and then you have that H, H, H. Now they're asking you for the molecular formula. Okay. How do we get the molecular formula? It's pretty simple, really. Count the number of carbons. How many carbons are present here? 1, 2, and that's 2. So that's 4. So it's C4. Then you count the number of hydrogens. That's 3 plus 1, 4 plus 1, 5 plus 1, 6. So it's going to work out to be C4H, what? 6. It's pretty strange. Yes, C4H6. Oh, geez, this is not 3. Sorry, this is 5. See, so that's 5. So that's 5, 6, 7, 8. So it should be C4H8. All right, C4H8, because that's C2H5. All right, so that would be the molecular formula of the compound, and that is how you would work that out. Remember, you can stop and ask questions. Then now let's see what the next thing says down here. Wait. Write a balance equation for reaction 3. Okay, so you need to write a balance equation for reaction 3. So reaction 3 is combustion, and the formula of compound A is C4H8. Combustion means that it reacts with oxygen to give carbon dioxide and water. So remember how I told you how to balance this? There are 4 carbons here, so put a 4 there. There are 8 hydrogens here, so you put a 4 there because it's 4 times 2, 8. 4 times that 2, it's 8. Then you balance the oxygen. This is 4 oxygens plus 4 times 2, 8. That's 12 oxygens, and you put a 6 there. 6 times 2, 12. Then everything in this equation are gases. All right, because it's combustion. Combustion is done at high temperatures. So the water is not going to be a liquid, it is going to be vapor. Okay, so that's that reaction. All right, so now it says describe a chemical test that can be used to distinguish between compound A and compound B. So we have to go back up. Compound A is an alkene and compound B is an alkane. So how can I distinguish between an alkane and an alkene? Well, here's the situation. An alkene burns with a sooty flame. Soot means that, you see, like if you ever see tire burning, right? There's this black part of the smoke. It's black, we call it soot, right? Alkenes burn with that sort of flame. It's like a yellow flame, yellow-orange flame. Colors are not my thing. So it's yellow-orange with a soot. Alkanes burn with a blue flame. So that's a nice little way of distinguishing between an alkane and an alkene. Just simply burn them. If you have a gas stove and you are burning your alkane, you notice it has a blue flame. However, when your gas soon finish, you notice that the flame kind of starts looking yellowish. The pot might get black because of the soot being formed. That's because you don't have enough oxygen, so it's incomplete combustion, and you kind of getting that sort of thing happening. But alkanes burn with a blue flame, nice blue flame. You know what I'm talking about because they have a gas stove. Then now, another way you can distinguish it is by reacting both compounds A and compound B with a halogen. All right. React both of them with a halogen in the dark. The alkane needs light to react with the halogen. If there's no light, no reaction takes place. But the alkene will react with the halogen whether there is light or not. So in the dark, it will react with it. So if I react compound A and compound B with bromine in a box in a dark room, and I get a reaction out of one, that tells me that this is my alkene. The one where there's no reaction, I know it's an alkane. Okay, so that's another way. Another way you can distinguish them is by combining both of them with acidified potassium permanganate. Now, when you do that, the alkene will react with the potassium permanganate, and you're going to get the potassium permanganate is going to change from purple to colorless. I spoke about this earlier. Potassium permanganate is a very strong oxidizing agent. So you're going to get, it's going to change from purple to colorless. The alkane will not react with the potassium permanganate. So that's like what? 3 ways how you can distinguish between the alkane and the alkene. All right. So we will proceed again. This question is a nice question. Then now it says list 3 characteristics of a homologous series. We did this earlier when we said they have the same general formula, they have the same general reactivity, or they react with the same things. There is a gradation in physical properties as you move along the series. So you move from gas to liquid to solid. They differ consecutively by CH2 or CH4, right? They can be prepared in the same general way. So when you see these sorts of questions are the questions that they may ask you for as an introductory question to organic chemistry. Can you say something so I know that you're there? Hello?
Sure.
Okay. Okay, draw the fully displayed structural formula for compound A, which has the molecular formula C3H8 for compound A. C3H8. Okay, so draw the structural formula for a compound C3H8. So of course, since it's C3H8, you draw 3 carbons in a straight line, then you attach hydrogens and make sure it's 8 hydrogens. What you're looking for is that carbon has 4 bonds around it and each hydrogen has only 1 line going towards it. Okay, and that's the case here. That's 2, 4, 6, and the 2 at the ends make 8. Okay, so that's C3H8, which makes it an alkane. All right. State the homologous series to which A belongs. I just said it is an alkane because it would fit into that. It would fit into that molecular formula, general formula of alkanes. Alkanes is CnH2n plus 2, and the formula is C3H8. So if I replace N with 3, it becomes C3H2 times 3 plus 2, which makes it C3H8, right? So it's an alkane. So you can actually work that out. So we're going to move on. Write the molecular formula for the compound which has 5 carbon atoms of the homologous series. So if it has 5 carbons, then it's going to be C5H12. C5H12. Remember, the general formula is CnH2n plus 2. You replace it, they said 5 right there. So you replace N with 5 and you work it out. C5, 2 times 5 plus 2. And that gives you your answer. Okay, so draw the fully displayed structural formula for compound B, which has the molecular formula C3H6. C3H6, so that would be an alkene. So you draw 3 carbons in a straight line, right? And then you attach a double bond to one, put a hydrogen there, one there, one there, one there, one there, one there. So there you go. See? So that's 1, 2, 3, 4, 5, 6 hydrogens, 1, 2, 3 carbons. And that's how you know you're doing well. All right. And then you state the homologous series to which B belongs. It belongs to the alkenes. Write the molecular formula for the compound which has 5 carbons of this now. So since now the general formula of alkenes is CnH2n, you replace 5 with N because it did say 5 carbons. So it's C5H10. And that would be the molecular formula of that compound. All right. For each of the following homologous series, write the general formula. What's the general formula of carboxylic acids? No. And what's the general formula of alcohols? So the general formula of carboxylic acids is Cn, and this might change depending on which book you're looking in. Cn minus 1 H2n minus 1 COOH. That's what I always say. Right? Alcohol is CnH2n plus 1 OH. The name of the first member of the series. So the first member of the series would be a compound with 1 carbon. Now, if it has 1 carbon, go ahead.
So you have Cn minus 1. How is that, sir?
Okay, that's what I was going to explain.
CnH2 plus 1 instead of minus 1. That's what I always see.
That's what you always see, right? And I disagree with that. But let me show you why I disagree with that. No, it says the name of the first member of the series. I'm answering your question, all right? The first member of every series except for alkenes has 1 carbon, because the functional group of alkenes is carbon, double bond, carbon. You need 2 carbons for it to be an alkene, at least 2. Well, for all others, you can have 1 carbon. So the first member of the carboxylic acid group is methanoic acid, which has 1 carbon. Bear in mind that this is a carbon. Okay, so this is actually already the carbon which is present in it. Now, since it has 1 carbon, you're going to replace N with 1. So that's 1. 1 minus 1 is 0. 2 times 1 is 2. Minus 1 is 1. Agreed? So the formula would be HCOOH. You see that? So that's how we end up with that. You mentioned that you have seen where the formula of acids is what? CnH2n plus 1 COOH?
Yes, sir.
All right. So let's say now we're doing that for this species where carbon is 1. In that case, this would be C1, right? 2 times 1 plus 1, 3. Because that's 2 plus 1, 3. So this would be H3. So you'd end up with CH3 COOH. And that's not right. That's not methanoic acid because it contains 2 carbons. All right. So that is why I use the formula Cn-1 H2n-1 COOH. We're going to try that now with 2 carbon atoms, 2 carbons. So if it has 2 carbon atoms, what we're going to do now is say this is 2 minus 1, 2 times 2 minus 1, right? So that's 2 times 2, 4 minus 1, that's 3. So that would work out to be CH3COOH. There you go. Okay, so that's how we end up with that formula. To be honest, you may not see this in a lot of books. To be honest, you may not see it in a lot of books, but that's the formula that I use. And your examiner cannot mark it wrong because it is actually correct. Okay, but if you feel very comfortable and confident in using the one that you see in your book, then you can do that. But we'll have the discussion at this level. So the name of the first member for the alcohol would be methanoic acid. The acid would be methanoic acid, and this one would be methanol. Okay, remember the general formula of alcohols is CnH2n plus 1 OH. So since it's 1 carbon, that's 1, 2 times 1, 2 plus 1, 3. So this becomes CH3 OH. CH3OH. Okay. All right. So that's that. That was in 2020. So let's look at this other question now. Compound C is a sweet smelling compound which is often used in flavoring and perfumes. Once you see sweet smelling, ester, think ester. And by the way, there's the functional group of the ester right there, COO, right? So once you see COO in the middle of a compound, you know that it is an ester. Okay, so another thing I want to show you is that an ester is made from an acid and an alcohol. I can separate the ester here. And this is my alcohol portion, and this is my acid portion. So all I would need to do to determine the acid that it comes from is add a OH right here. And to determine the alcohol, I put a H right there. So this is actually propanoic acid, and this is methanol. Now, if I want to give the name of this compound now, let me clear all drawings. If I want to give the name, I would need to separate it into acid and alcohol again and name the alcohol portion first. The alcohol portion contains only 1 carbon, so that is meth. And to that, you're going to add il, so it's methyl. Then the acid portion contains 3 carbons, so that's prop. And then to that, you add an O8, methyl propanoate. Okay, and so we would have cleared up a lot of things there. So it's a state the name of compound C and the homologous series to which it belongs. We just did that. It is methyl propanoate and it is an ester. Draw the fully displayed structural formula of the 2 molecules that are produced when compound C is hydrolyzed. So hydrolysis means that you're using water to split compound C into what made it up in the first place. And that is what I did earlier when I split it up, when I said, okay, all you need to do to determine what makes it up is split it right there, add a H there and add a OH over here. And that basically, if you draw this like that and draw this with the H there, that's what they're asking you for downstairs. Okay, and that would give you the full marks right there. 2 marks, very little still. But anyway, 1 mark for each. So let's look at this part. Ethanol is widely, give me a second, get some water. Ethanol is widely used as a solvent for making cosmetics and perfumes. So there's ethanol being converted to an acid. We know it is an acid because we can clearly see the functional group right there. COOH. See? COOH. There you go. So it's an acid. State the name of compound D and identify the reagents and conditions necessary for ethanol to be converted to compound D. Well, this is an interesting question. It is ethanoic acid, and it is an acid. How do I convert ethanol to an acid? Well, here's what we use. We would use acidified, acidified potassium permanganate, right? Good. Acidified potassium permanganate, and we would heat it. Triangle means heat. Now, when you heat the ethanol, what's going to happen first is that the ethanol right here is going to be converted to an aldehyde. And then when you add more acidified potassium permanganate, it's going to be converted to the acid. So this is actually the oxidation of alcohols, right? So you're using an oxidant to do that, which is, as I mentioned, and this is like the third time I'm saying this, or fourth time, potassium permanganate is an extremely powerful oxidizing agent, okay? And it's always used, even at the highest level of chemistry. So we proceed. That was in 2020. Explain how ethanol can be made from the fermentation of sugar. I'm not sure if you're getting this, but I'll still go through it. Include the chemical equation for the overall fermentation process. Fermentation basically occurs where you use you use an enzyme in yeast called zymase. And what you do is you respire glucose anaerobically. Now, there are two types of respirations for those who do biology. Respiration may be done using oxygen, which we call aerobic respiration, and there's anaerobic respiration, which is without oxygen. When you respire anaerobically without oxygen, using sugar in the body, lactic acid will build up, which is what you call cramp. If you ever run at sports there, if you're playing or whatever the case might be, and you feel stitches, what you call stitches, it's actually cramp. It's lactic acid that is building up in your muscles, causing the cramping, okay? And the only way to get rid of that is to breathe. Now, if, however, I were to take glucose and I were to respire it or ferment it without oxygen, I am going to get ethanol. So I can take C6H12O6, which is the so-called formula of glucose, and I use zymase, and this is at about 37 degrees Celsius because you do not want to denature or inactivate the enzyme, and you're going to get ethanol, C2H5OH plus CO2, which is a gas. This is aqueous. Okay, so now basically you're fermenting your glucose in the presence of yeast at 37 degrees Celsius to give your ethanol and your carbon dioxide. And of course, you want to balance this equation. So let's see now, that's 12 hydrogens. Let's put a 2 here. So that makes it now 4, right? And if we then, that's 2 and that's 2 and that's 4. So if we put a 2 here, what does that now become? 6, that's 12. There you go. Good. So basically, this is what the examiner is asking you for. Explain how ethanol can be made from the fermentation of sugar. So you simply say that the glucose is mixed with zymase, not zymase, with yeast, which contains zymase at 37 degrees Celsius. And this is without oxygen. And then after some time, you're going to see bubbles and you're going to get ethanol forming after that. Okay? They may not give you this. State one other use of ethanol. So up here, they say ethanol may be used they said it was used for as a solvent for, there it is, for making cosmetics and perfume. But what else can we use ethanol for? Or what is ethanol mostly used for in the world? Anybody? What do you use ethanol for, guys?
Rum production.
Rum production, there you go. Right. So it is used in alcoholic beverages. You won't lose marks for saying it, and nobody will think that you're a rumhead if you do. Okay, so let's look at this next one now, and then after this one, we will press on to the next aspect of our thing. Okay, Ethene undergoes halogenation reaction to form 1,2-dichloroethane. Draw the fully displayed structure of ethene. So we're drawing ethene first. The F tells us that it contains 2 carbons, right? The ene tells us that there's a double bond there, and then we add our 2 hydrogens. Right, so, and that's that. Not bad. Then now we say, draw the fully displayed structure of 1,2-dichloroethane. So all that happens with the ethane is that the double bond breaks and you add the chlorines across it. So that was your ethane with the double bond, right? It's gonna break and you're gonna add chlorine there and chlorine there. And then you just put in the hydrogens like that. Okay. It says, is the halogenation of ethane an addition or substitution reaction? In other words, this should be clear. Did you add the chlorines to the ethene, or did you replace something in the ethene? Bear in mind that this is what ethene looks like, right? That's ethene. Now, did you add the chlorine to it, or did you replace the hydrogens? You clearly added the chlorine. So this is an addition reaction. And so I will just pause there to say that alkanes undergo substitution reactions because they are saturated. They have the maximum number of hydrogens that can hold on the molecule. Alkenes undergo addition reactions because they are unsaturated. Okay? And so that is what they're really asking you about right there. Okay, so we proceed again. Dichloromethane can be obtained from methane, right? This reaction takes place in 2 steps. Write balanced chemical equations to show each step in the formation of dichloromethane. So dichloromethane is being formed from methane, okay? And this is a halogenation reaction. You're adding chlorine to the methane. For this to happen, you need light. So it takes place in stages. First thing you want to do is you want to draw your methane. So this is methane, okay? And it takes place in stages. So I'm going to add to that chlorine plus Cl2. This is Cl2, but I've split it into this like that. And what happens is that this chlorine is going to replace one of the hydrogens. So let's say it replaces that. What we end up with down here now is CCl, H, right? Plus HCl, because the hydrogen is going to then combine with that chlorine. So you get HCl, right? You then take this this species now and combine it with another chlorine molecule, okay? And this one of these chlorines is going to replace a hydrogen. So let's say it replaces that. And what we're going to end up now with is CHCl, Cl plus HCl. Because remember, the hydrogen here is going to then combine with that one. And that is your 2-step process for that reaction. Okay? Yes?
Yes, sir.
Okay, so we proceed again. Is the halogenation of methane an addition or substitution reaction? They're basically telling you, because from up here we did the addition. So this clearly is substitution because you're replacing the hydrogens with the chlorine. Okay? And we're going to pause it there for the organic chemistry, and we're going to move on now to the next aspect of things. Let me see what that was. That would be metals and non-metals. So that is the organic intro, and that's a reaction of organics. And so now we're looking at reactivity and extraction of metals. All right, and then non-metals and non-metals. Let's just say, first of all, that there are two, for the most part, two metals that you need to know how they are